So thank you for the organizer for this very nice conference and for invitation to talk here. So we already heard here about many things, and in particular this for the topological side, quantum topology side, these VRT invariants, for example, in the talk of Sergey. So my introductory remark will be that this WRT, they use only small part of the representation category of quantum SL2. So use in fact, very partially. QSL2 at Q 2P equal 1. In fact, here it uses even restricted quantum SL2. And here, to be more explicit, only simple module, so reducible module, x dot. Somebody used V, but I use x here because I will use V for something else, to xp minus 2. And here we will, a lot of people would like to categorize this, focus on this. And my message will be from quantum SL2, from variant of quantum SL2, we can build a wider scope of quantum invariants, which maybe would also like to be categorized. And some of them are involving abelian flat connection. And for the people following Sergey lectures, we add such thing in this Q series formula. So then I will consider here two versions of QSL2 and corresponding quantum invariant. First one is unrolled. I will give detail. And this will lead to invariant of 3 manifold with abelian flat connection. And then I will switch to quite new stuff where we take the non-restricted. And here, what we get at the moment is invariant of links with SL2C flat connection. Yes? Oh, sorry. I can't do this. Okay, and in fact, it's up to gauge, so we should think about this as function on the character variety. And it should be related to something else, but it's not extended to 3 manifold, but maybe this project will continue. So first, today is another day. Yesterday we had lectures by Katarina and David where this quantum SL2 was defined, but it was the Lustig version with divided power. And I insist that here I'm not using the divided power, and it will be this Cax de Concini version and some quotient of it. So let's consider. So I will say a few words about this. In fact, it at Q equal EI pi over P. P is greater than 2. And eventually, I do not choose only Q, but I fix its logarithm. And I will use the Q alpha equal EI pi alpha over P for any complex number. And now this quantum group I've just denoted U UQ SL2 is just the specialization of the generic version. So as algebra, you have generator KEF. You know the relation KE Q2 EK. This is completely usual. Bracket EF K minus 1 over Q minus 1. And then you know that this guy has Hopf algebra structure. Everybody knows. Sometimes you have certain coproduct or opposite coproduct. So for people, I just write this delta of E, which is 1 tensor E plus E tensor K, and blah, blah, everything. So we have this very well known Hopf algebra structure. And even if, at a root of unity, again, note that EP is not 0 here. It's not forced to be 0. It's not necessarily nilpotent. So this Hopf algebra has a quite interesting center, and this is key point is in the discussion. And this center contained, and this is a degree P extension, a nice Z dot, which is a abelian Hopf subalgebra. So this is generated by KP AP FP. It's easy to check that these guys are central. Okay, so now this guy with no other relation will we call non-restricted. Okay, and in the first part of the story, okay, I will consider nilpotent quotient. Let's start here. I will put a bar, and for the moment this will be just U, where we forced nilpotence. But K is still free. Okay, and here we have highest weight module. Say V lambda, where the highest weight is Q to the lambda. And this lambda is a priori a complex number. If I take a generic complex number, if lambda is integral, then you recover the well-known story with integral weights, and it's a little bit specific. So I will focus, on the generic case. And if you do this way, then this V lambda is equal to V lambda plus 2p. And the fact that over this version you get this isomorphism or equality is a little bit a problem. So we would like to work with braided category or ribbon category. So we will consider the category as finite module over this guy. But in fact, we have better consider this guy, this category is not braided. So this U bar mod is not braided. And what we call unrolled will give a braided extension of this category. So formally, so we build a braided extension, and the motivation for this braided extension is to break this equality by adding a new Cartan generator. Okay, and formally, this will be on hold, so we will denote U bar H, and it can be formally defined as U bar semi-direct product with U of H, where this H is a Cartan of classical SL2. This means, and you can define the action, so this is, in fact, this unrolled category is was implicit for a long time, even in Otsutsuki book, the R matrix is involved in this category without explicitly giving the extension. Then some people just say, you just add, an H, and in Carbonis thesis, then this is defined nicely with a semi-direct product. What does this mean? This means that you have a new generator H, and which commute with K, and then which acts, which has a classical relation with E and F. Sorry, bracket HF equal minus 2F. And then a weight vector. So here we are considering the category where we've got, we will ask Q to the H to have the same action of K. Sorry? This one is universal development algebra of the Cartan of SL2. So it has just one generator. It's at the root of unity. Yeah. I don't need to complete. I just say I take this algebra and I take weight modules where the K weights and the H weights are connected by exponential. I don't need the group. Sorry? Yeah, but I do not pretend I take all modules. I take just my purpose. Here we will work in a case where the category has the structure of a group category, and contrary to Anna's talk, I will work on the representation side. It is very likely that using this notion of Hopf group algebra, this can be nicely reformulated in terms of Hopf group algebra, but this is not done for the moment. So I'm interested in the category. I do not pretend. So I consider C to be the full subcategory of this guy, where objects are weight module, where K acts as QH. This means if H V lambda equals lambda V lambda, then K on V lambda is Q to the lambda V lambda. So I consider weight module over this semi-direct product such that the weights are compatible in this way. And this is the category. And in fact, in this category, you just break this isomorphism. And now the good point here is that this category is ribbon, and this is the starting point for CGP invariant. So this CGP is for Costantino Guir-Paturo invariance. So this C is ribbon, and maybe it's good to understand why we took this category to write down explicitly a formula for the R matrix. And this is written as Q H tensor H over 2, sum over n, 1 square, 2n over n factorial, Qn n minus 2, n minus 1, and Enfn. And in fact, we are not interested in the sense of this guy anywhere. We understand this as an operator on a tensor product of any finite dimensional module. And here, this bracket M is, even it will work for lambda in a moment. It's Q lambda minus Q minus lambda. And this Q H tensor H over 2 acting on V lambda tensor V mu is equal to Q lambda mu over 2 times V lambda tensor V mu. Okay, so we have formula, and the category is braided. So there is one more nice feature in this category, is that you may consider the weight mod 2 and then you will see that this category has the structure. I don't say, some people say a graded category, but this is not good. Usually in a graded category, you have grading on home spaces. So I would say a group category with group C over 2Z. And then this is our ingredient. So first, because C is ribbon, and that was explained in the previous talk, you have Reshetikhin 2IF ribbon functor. And this I denote by F. And this goes from, let's say, C colored tangles. So each string is colored with an object is a category. You preferred object, which are the simple object before, to the category C. And there is a bad feature, which is for link evaluation. So usually for link, you get the Jones polynomial, a scalar. But in this case, because we are working with a root of unity, so evaluation is 0 if V lambda is used. And in some sense, this is bad, but there is a solution for this. I will not give detail, just I mention that modified trace theory developed by Guirpaturo and colleagues solves this. And in this case, it's rather easy. Let's say, suppose that L is a link, colored link, colored with object in this category C. I just put L for being short. And then I open this link. I open any strand. And then I see here a V lambda color. And the link is just the closer. So suppose L is like this. Then this functor, Reshetikhin 2IF functor, will assign to this an endomorphism of V lambda. And V lambda is a simple representation, so you get a scalar. times identity of V lambda. And then this modified trace invariant, denoted with a prime, is this scalar coefficient corrected with a certain d lambda, and this d lambda is modified dimension, and it is cooked so that what you get here doesn't depend on the place where you cut it. And this d lambda is a modified dimension. The formula, this comes from modified theory. There is up to scalar a unique modified trace in this situation, and you have only to choose the normalization, and it's here it's normalized this way for certain reason. It's interesting to see where you have denominators if you think about categorification. And so we get this evaluation. And the second point I already mentioned is this group category structure. And it says that you can take alpha in C over 2Z and consider C alpha, which is a full subcategory whose weights are alpha mod 2. And then we get a group category, which means that tensor product is homogeneous, and all morphism, non-zero morphism, are homogeneous. Sorry? No, it's mod 2. Remember that, very good question. If you take this V lambda, then you start with a V lambda here, and then you go down by F, and you step by 2. So if you want to grade by the weight, you have better take mod 2. Okay. And then, what I say is that it's a weight, all weights, all weights. But if you do tensor product, then you are coherent with this. So this C alpha in C over 2Z is so-called group category, or graded for certain people. And this allows to use this grading for topology. So now we start with this topology. A little bit of topology. So if M is obtained by surgery on a frame link as usual, then, and I say with flat connection, it will not be immediately a flat connection, but people used to this will recognize. We take a homology class on M with coefficient in C over 2Z. And here, remark that from this you get FC from pi 1 of M to C star obtained by sending gamma to EI pi gamma, C of gamma. Okay? And by this I mean that I will work with cohomology class mod in C over 2Z, but this is exactly describing C star flat connections. This is the same. And it's just more convenient to work with this C over 2Z for relation with the weights. So then, let's give an example. Sorry. Now, what about the description of this H1 of M with coefficient in C over 2Z? This is a basic algebraic topology. And if you take C here, then you can go to C over 2Z forward number of components of L by sending C to CG, which is C evaluated on the meridian of the G component. And then you get a bijection from this. So the image, it's a bijection. Let's change this. If you remove this and takes kernel of B times C over 2G, or the C over 2Z, where this B is Linkin matrix, then it's elementary algebraic topology to see that you get a bijection. And this means that you have a combinatorial description of those flat connections. So now we work with, as usual, maybe I work out an example. Suppose M equal S3 of Ka, and this, I just say this is a framing coefficient. If A equals 0, it's easy to understand. If A is non-zero, how it works, then you will get H1 of M with C over 2Z coefficient, which corresponds to the 2K. You take the kernel of multiplication by A in C over 2Z. So this is class modulo 2 of those guys, and the K is in C over AZ. And of course, this is Z over A as a group. So now we can use Kirby-Callas. A Kirby-Callas will be assigned precisely to a complex, rather to the class mod 2. No, the kernel, I send, if I take a homology class, I can evaluate on meridian, and I get element of C over 2Z. And then, a priori, the image is inside this, and I state that, and it's really an elementary exercise, the image is the kernel of this linear equation. This is a matrix. This is the image, and it's bijective on image. Okay, is it clear? You're welcome to ask questions. This is useful. You have, if you are on topological side, usually this comes very quick. If you are on a representation theory side, you know that this exists, but maybe it's not so clear, so you just have to do the exercise as a master student. It's not that bad. Okay, is that okay? So now the problem is to use this combinatorial input, a link, a framed link, and a coefficient of a homology class in order to give a formula which will define an invariant. So if I take alpha in C, you know that we are interested in certain linear combination of color, a magic combination of color, which will be invariant by sliding. And indeed, here you can do the sum for J equal 0 to P minus 1, and you take a modified dimension times V alpha plus 2G, and the corresponding modified dimension. So this will be the graded Kirby-Callas. And indeed, suppose this is for alpha in C minus Z, generic. Else I should do something else, and it's not obvious. But we work generically. Suppose for all G, CG is not 0 or 1, non-integer. Then I will say that's good presentation. This I'll call the good presentation. Then I can evaluate and get the following theorem of those guys, CGP. I worked with them afterwards, but they did this. Suppose P is greater than 2, and P is not 0 mod 4. Then what you can do is define CGP with this C, and this will be F prime of this link where each component is colored with the corresponding Kirby, and this tilde is just for your preferred lifting CG. Here, CG tilde is lifting in C of CG, which is in C mod 2Z. So you take any lifting, the theorem says that the result will be the same if you change the lifting. Okay? Then you need a normalization. And this is an invariant of MC.
Condition on CJ not being 0 or 1 somehow related to spin C structures that come from spin?
No, not yet. The condition. So this I will give several remarks with this. Maybe I should erase, but think about it. In fact, if you fix this abstract C, then you can have different presentation. And some will be good, some could be not good. And the point, the remark, the lemma is that if C is a non-integral class, which means at least once is outside 0 or 1 as evaluation, then there exists a good presentation. Okay? So this means that this invariant is defined for admissible MC, which means for all non-integral C. Okay? So I erase, you can think about it, and I will give a little bit more. So exactly, I will make explicitly the remark now. So this is remark 1. In a MC C non-integral, and this means X gamma, that C of gamma is not in 0, 1, has good presentation. And second remark, remark 2, this can be done with colored link. So you can define CGP of a three-manifold, a colored link, and C, where C is a connection on the complement of L. This can be extended. Okay? And then, in fact, this invariant is defined for admissible triple, and admissible triple sorry, it's implicit here. I should ask that the color of L is coherent with C. Okay. C, I would say compatible with coloring. And this means C of a meridian of certain component of L is the same as color of component.
But you need this extension, you have to lift to C more than C.
Yeah, but it doesn't depend at the end. It doesn't depend. It's part of the theorem. Okay. It's not exactly true that you have a periodicity, but the effect of the Kirby color satisfies this periodicity. It's because you are in the kernel of the linking matrix and the contribution is controlled by the linking matrix. Is it clear? Okay. And what is being admissible? It means either C is non-integral or L contains a projective color. Here I'm quite general. If you want, all the generic module I wrote here are projective, but you can use all modules, including those with highest weight, including those which are not simple. But admissible means you can find somewhere at least one projective color. Okay? And now, third remark. See, we add TQFT extension. As a symmetric monoidal functor on a certain category of admissible cobordism. And in fact, Dorenzi, with my student, obtained two TQFT and generalization with the appropriate modification on of the definition of modular category. I will not speak about this, but I want. Sorry, yeah. Yeah, 1 plus 1 plus 1. I mean a two functor. It's not quite that, no. Because in Tourayev, you do not have this modified trace contribution. The problem with Tourayev-Virlisier is that you have a good formalism, but not really a lot of examples. Here, we are starting from the example. This is the point. Thank you for the question. Okay. And then there are two more remarks. So we have a theorem which is in this paper, which consider the case P equal to. And in case, I already explained that to a cohomology class correspond a flat connection. And if you take this abelian flat connection, so you have this Redmeister Tourayev torsion. And this is and then what we get is that this is CGP at P equal 2 of MC times a normalization, which is of the form Q, 1 plus B1 of M. And here there is still the normalization of this torsion uses a spin C structure, whatever it is. And then you have here a small quadratic contribution, C sigma of C. And this is a quadratic function defined by Delou and Masuyo. And the striking fact is that in order to normalize the torsion, 2F is using spin C, and here we have a normalization which do not use, which get rid of the spin C structure in the normalization. With this guy is an invariant of the spin C structure and the homology class, and it just measures the relation in between. And we also, with the same guys, in case P 0 mod 4, we get similar, but this time is this with C in spin M with coefficient in C over 2Z, and I will define this guy. It's a notion of generalized spin structures, which is very near the torsion spin C structure used by Sergei. And so maybe I need a little more space. So if you start with M, then you have tangent space, and this is the principal bundle, oriented principal bundle, with fiber SO3. So then this spin, M C over 2Z, is defined as a subset of H1 of PTM with C over 2Z coefficient, and it's just those sigma, so that restriction to the fiber, so the fiber is SO3, is non-zero, is the generator. So then you have also, not as a kernel, but a linear equation description, and you can build invariant with this. What is the difference with the previous situation? The difference is in the vanishing or non-vanishing of the stabilizing correction. And the computation tell you the alternative. And then, okay, that's okay. One remark is that you have here a Bochstein map going to H2 of PTM C over 2Z. You can define similarly spin C structure inside this group. And the Bochstein homomorphism give you a map from this generalized spin structure to the torsion spin C structure. So in this sense, these spin structures are refinement of Sergei torsion spin C structure. Okay. So I have a little bit of time to sketch what happened in the non-restricted case. Are there questions on this part? So we get from unrolled quantum SL2 invariant of manifold with abelian flat connection. And for the small root of unity, we already get a strong thing. It is known by different people, including Viro, that this case recovers multivariable Alexander, but here we do recover the torsion. Yeah, David? Yeah, because the divided powers forces K2P to be 1. Right. And this forces integral weights. Right. So the key point here is that we have a version where we have a moduli space of weights. And it will be even wider now. Okay? So now, non-restricted QSL2 and SL2C. So I will try not to be technical and to give you the strong ideas of the construction. So you have two sides, and you have to connect the two sides. One side is quantum group. The other side is topology, flat connection or similar thing. And then you have to connect. And so we start with this Z dot equal KP EPFP, include in Z. And then the proposition, which was known for a long time. I think it was already in Kac the Concini, but that was revisited by Kashayev and Reshetikin, is that this Z dot is isomorphic to C of an algebraic group G. We just have compared the coproduct. So it's abelian Hopf algebra, and this G is given by pair of matrices 1, 0, phi, kappa, 1, epsilon, 0, kappa. And I look at this in GL2 of C times GL2 of C opposite product. And the correspondence is by kappa goes to Kp, epsilon goes to 1p EP, and phi goes to, here you have to change a little bit, Kp Fp, and the proof is compare coproducts. So we have identified, and this is good because then the spec of this guy is this group. Okay, I have to erase. Maybe this one first. So we are not far from connecting characters to SL2C. And this is really the point. One. So this way we see a map here, sorry, can put here, to SL2Z, which send AB to A B minus 1. So now, what is the picture? We start with X, which is the spec of the full center. Then, by restriction, we go to the spec of Z dot, which we can identify with G. And then, by this psi map, we go to SL2C. And I will denote by phi the composition. big phi. So now, if we follow Kashayev-Reshetikhin, then there is a map B from x times 6, x cross 6 to x cross 6. You start two characters, and the category is not symmetric here. But you understand the defect. In fact, it's not exactly, this map will be a rational map. So it's only defined outside the vanishing of a certain element W. It's only generically defined. It sends AB to B prime, A prime, and it's defined that so that VA tensor VB is isomorphic to VB prime tensor VA prime. So he tells you how to not be symmetric. And it's a solution of Yang-Baxter equation. You have a notion of compatibility at a crossing, which is given by this B. And then what we did, so with volume form on the V lambdas, so how braiding will be defined for an object. Of course, it's clear probably for algebraists that if I fix a character, then this will define a simple module. Okay? And this VA is the simple module. That was my previous V lambda, but now the character is slightly more complicated. And we can fix the ISO up to P2 root of 1. So at the moment, we are not able to have a strict holonomic braiding. We call this holonomic braiding. And this gives us what we call holonomic braiding up to same thing. And holonomic braiding means that you have the Yang-Baxter move, but using a braiding which change the objects. And if you take, for example, this relation, you start with EBC, you will go to A prime, B prime, it's better to take C prime, B prime, A prime. And here the intermediate are given by the map B. And on the, the holonomic braiding given by composition will associate to this an operator up to P2 root of unity. And if you change the other, maybe it's better to take one here. 1, 1, 1. And here I take the other one. And then I go to ABC, to A2, B2, C2. And so set solution of Yang-Baxter equation says the two are the same as the one. The B is compatible with this. And holonomic braiding means the operator is the same up to P2 root of unity. Okay, so just try another 2 minutes. From this, we get RT operator. And with modified trace, we get evaluation on diagrams. Okay? And I will be short on the topology side, except if you give me 2 minutes. On the topology side, So what we get here is take a link diagram. For the moment, it's just a diagram. Scalar with characters in a way compatible with this B map. Then you have an F prime evaluation. And the question here is, what is the topological meaning of this? In which sense is it an invariant? Okay, and here the intermediate thing is the notion of a quandle. So I will probably not have time to develop this, but a quandle is some kind of refinement of a group. And the good point is that, so I can give the definition. So a quandle Q like this. So it's an operation Q2 to Q, which is a self-distributive. Conjugation in a group is a quandle. And A like this is bijection. And A to the A equal A. And so what we do, and you have, for link, you have the quandle of L with a base point. This is refinement of pi 1. Okay? And you have a notion of quandle representation. Okay? And the fact is that X, I will just say in 2 words, X is not a quandle, but is a priori a biquandle. In some sense, quandle is something like B, where the modification is only on one of the two. When you have, so let's say, X, you go from AB to B prime A prime. So this will be something for a biquandle. But in a quandle, you will put AB, keep A, and here do A to the B. So this is for a quandle, this is for a biquandle. Then, by a result of Lebed and Van Dramin, Q equal X has quandle structure. And what do we do? Let's then the evaluation I'm mentioning here is an invariant of the link together with a quandle representation in Q. So at the end, we have, so it's a theorem of all these guys, so B, G, P, R. Invariant of M together with Q-link. And a Q-link means a link together with a quandle representation here. And because of the phi map, this Q-link structure by the phi map induces, this is also a theorem, that the phi map is a quandle morphism to the conjugacy of SL2. So this Q-tangle induces an SL2C representation, connection. In fact, this is of Q-links, I'm cheating, up to gauge. I'm cheating a little bit, but you should have in mind that from the quantum group, the full thing, you get a set of characters, and on this set of characters, you can show that there is a quandle structure. Biquandle is done for diagrams. Quandle can be made topological. So naturally, you have biquandle. By this correspondence, you get a quandle. You can work with quandle representation, and this quandle representation contain implicitly a flat connection, an SL2C flat connection. That's all. Thank you.
Questions or comments? Can you say a little bit more about this function psi c, or psi sigma c, the one associated with a spin C structure?
The man?
Yeah, I mean, for example,
Yeah, sure, for sure. Sure. You start with the linking matrix. Let's say, then you have a linear equation. So you can do B C1 Cm, and here you put, so it's in C over 2Z, so it should be the C 1 over 2 Cm m over 2. So the solution of this linear equation corresponds canonically to these spin structures. You replace the kernel by solution of an affine problem. Yeah, this is not very hard. In fact, the idea here is to understand the four manifold and the W2 of the four manifold for topologists.
Can I express the mod z value of that in terms of a linking form or anything like that?
Of what?
The mod, so psi sigma c is
I'm sorry. I was confused. Yeah, it's a rational number, yeah. I have the formula somewhere. It involves, so you have also better take the four manifold, and it's defined using the quadratic, it's defined using the quadratic form on the four manifold. It uses the quadratic form, so you lift the C to the four manifold in some sense. You take the square and correct with the W2 as usual. I have the formula, but it took me some time. It's in the paper. Sorry, I didn't understand the first.
So questions? So the question, does part of the story generalize to other groups, or is it?
It's done by people like Geert Paturo, De Renzi, for the abelian flat connection, for the first part. Okay.
I was thinking of the second part.
And the second part, I have no idea.
At the beginning, there's a similar story, at least at the beginning.
Yeah, it's true. That's, yeah.
But then
here, even we are not completely